Hello, Honors Physical Science kids, and welcome to class on Wednesday. We started waves yesterday. We're going to continue on with waves today. I know yesterday was quite a few slides of notes, like 20. This section is also a ton of slides and notes. We'll probably just get about halfway through it today. So you need to send me a copy of your notes. So you need to send me your notes, and that's actually all I'm going to make you do today, minus you are going to have to call and check in with me. So today, real simple, send me a copy of your notes, and you need to call and check in at some point with me. Be ready to answer a question about your notes when you talk to me. All right, so that's the case there. Hopefully, we're good with that. Okay, eyes looking pretty good today for me, after falling off the bike the other day. So that was exciting. Let's pray. Dear Lord, we want to thank you so much for bringing us here today on this Wednesday. Lord, as we're already halfway through the second week of virtual learning, we just ask that you just continue to bless us, continue to be with us, strengthen us, comfort us, encourage us. Lord, we want to ask that you just continue to bless the families and friends of those who have lost loved ones to this nasty virus going through and around our world. We ask that you just continue to keep our friends, our families safe and free from this virus. We want to ask that you just be with us as we're cooped up in our houses, as we have siblings, as we have parents, as we have different situations where we're not used to and we may be getting annoyed and bored. We just ask that you just continue to bless us, continue to be by our side, Lord, because we know that you're always there for us, no matter the time, no matter the situation, no matter what we are going through. I want to ask that you just continue to watch over, continue to bless us this day and every day, Lord. All this and all things we lift up to you in the name of your great and glorious Son, Jesus Christ. Amen. All right, so we're going to start section 2, characteristics of waves today. And as we go through, we'll be ready and set to go. All right, so here we go, section 2. So we got 4 properties, 1, 2, 3, 4, that we're going to talk through. Okay, so here's what they are. Amplitude and wavelength are measurements of distance. So we're going to be measuring those in distance. Normally, if we measure things in distance, you guys know we're going to be measuring them in meters. Okay, so a lot of times if I tell you amplitude, if I tell you wavelength, we're going to measure those in meters. Period and frequency are going to be measurements based on time. So our period, our frequency is going to be measured in time, and we'll be set and we'll be ready to go there. All right, so amplitude, wavelength, measurements of distance, period, frequency, measurements of time. All right, so here we go. Let's actually talk through what it is. Okay, so amplitude measures the amount of particle vibration. Amplitude, the maximum distance that the particle of wave's medium vibrate from their rest position. In a transverse wave, it's the distance from rest position to crest or rest position to the trough. So remember, transverse waves. Oh, what is a transverse wave? Let's see if we remember from yesterday. Transverse waves. Anyone know? We have transverse waves. Remember, particles are one direction and the actual motion of the wave is the other, so they are perpendicular. Remember, mechanical waves require a medium, electromagnetic do not. Transverse, we're perpendicular. Longitudinal, we are parallel. All right, so let's draw a transverse wave. We're going to draw a transverse wave up here. Okay, so we have our transverse wave there. A lot of times we'll have like that equilibrium line going through the middle there. Your amplitude is going to be from that rest position to the crest. Remember, the crests are the top, or the rest position to the trough. And those are going to be the same value as we go. So that is just your amplitude there. That is just your amplitude there. As we go through the wave, the amplitude should all be the same. So maximum distance that particles a wave's medium vibrate from the rest position, great. Distance from rest position to crest, rest position to trough, those distances are the same. And so that is what our amplitude is. It's just from the rest position to the top, rest position to the bottom, amplitude is there. So that's what we have for amplitude so far. All right, transverse waves have the shape of a sine wave. So I know we haven't talked sine, cosine, tangent. We mentioned it once or twice in class, but you haven't actually talked about it in math class yet. This is what a sine wave looks like. It looks like that wave that I've been drawing up there and that we drew yesterday. Okay, so those are sine waves, so sometimes we'll call it a sine curve. So when the homework in the next day or two, you will have to probably copy an image again or draw a picture of it and label some things for me. All right, so it's called a sine wave. As we go, that's what the shape of a transverse wave actually looks like. All right, it's like an S turned on the side. You guys can see that. Okay, so here we go. We actually have a picture. Now, what did we say? Hey, this was our equilibrium line. I don't know how to say that word. I struggle with L's and R's together. You guys know that. Equilibrium. I'll try it again. There we go. Okay, so here we go. What do we got? We got this sine curve. We know the crest is at the top. We know the trough is at the bottom. Hey, we have an amplitude here. Hey, we have an amplitude here. And if we look, our amplitude is just actually 1 meter, because from the middle to the top, from the middle to the bottom, we see it's just 1 meter. All right, wavelength. If you were to guess what wavelength meant, you probably would guess the length of a wave, and you would be correct. Okay, so wavelength is just going to be the distance from any point on a wave to an identical point on the next wave. All right, in a transverse wave, the easiest way is to tell crest to crest or trough to trough. All right, so let's talk through this. As I look, I could look here. Okay, then we go all the way up, all the way down. When's my next wave start? Right there. Okay, when's my next wave start? Right there. Okay, so this would be one wavelength. That would be a second wavelength. We're actually going to measure it in meters probably as we go. But let's talk. It said crest to crest. So if I look there, I'm going to draw actually the symbol for it too. Symbol for it is called a lambda. So if you want to enter that in your notes, I would go insert special character, and then you're going to type in lambda, L-A-M-B-D-A. It's a Greek letter. We're going to talk through that on the next slide, and the next couple of slides. All right. So we said, hey, that's a wavelength. We could also go from a trough to a trough, and that would also be a wavelength. Those will be the same. Now, if I'm talking a longitudinal wave, where do you think the wavelength is going to be? It's going to be from a compression to a compression, or a rarefaction to a rarefaction. All right, so those are going to be my wavelengths there. So on a transverse wave, we're going crest to crest, or we're going trough to trough. And then, hey, you're going to notice a lot of this is the same, but in a longitudinal, we're going compression to our next compression, like we talked about. Hey, compression, remember, is compression where they're all scrunched up, to compression where they're all scrunched up, rarefactions where they spread out, to rarefaction where they spread out, and that is going to be what I have for my wavelength. So far we have amplitude, which is your distance from the equilibrium to the crest or to the trough. Wavelength is one wave, and we go from an identical point on a wave. So normally it's really easy to go crest to crest, trough to trough, and we'll be good and we'll be set there. Next thing, I already mentioned all of this, so this isn't new. Let me get out of your way here, and I know this light is a little weird today, and I apologize. So if you're having real issues, please let me know. All right. So here's what we got. When using the equations, we're going to represent it with a lambda. Like I said, just insert special character, type that in, and you'll get that thing. If you just click on it, it will pop up in your doc. And we know it's going to be measured in meters. Why? Because distances are measured in meters. None of that is new information. All right, so hopefully we're okay on amplitude. Hopefully we are okay on wavelength. All right, so let's continue to move on. All right, actually, let's just real quick. I drew these up here, but hey, crest to crest, good. Trough to trough, good. That is one wavelength. Okay, so if you can't see that, let me just trace over one more time. Boom, 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 boom. Okay, crest to crest, one wavelength. Trough to trough, one wavelength. Not new information. Same thing here. Hey, compression, compression, one wavelength. Rarefaction, rarefaction, one wavelength. Okay, and so that is what we have for a wavelength. Identical parts, and we'll make sure that we're good. All right, next slide coming up. Let's start to talk through period. I need to go grab, for some reason my Windex is in the back of the room, so let me grab that and erase the board for us. We're going to leave those pictures up at top because we might need them again at a later point. All right, so let's talk. We've talked through a whole bunch and kind of reviewed through some wave stuff. Like I said, be ready for me to ask you a question or two when we talk throughout the course of the day. Hey, just so you know, you can't talk at 11 to about 12. I'm doing a review for my honors chemistry kids, so we can't talk during that time. All right. Period. Here's what a period is. The time it takes for a complete cycle or wave oscillation to occur. Time required for one full wavelength of a wave to pass through a certain point, represented in equations by a capital T. Okay, so period is a capital T. It's going to be measured in seconds. Now, we did this a little bit the other day when we were talking pendulums. Remember, what was an actual pendulum period? Pendulum period, if I started over here, the period would be stop. Okay, so when it gets back to the stop place where it started, that would be one period. Okay, because it's one complete cycle. So period, 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 right? So that's what a period is. How long it takes for one actual cycle to occur. Okay, so period, capital T, it's going to be measured in seconds. All right, so that's what we have, what a period is. And if you think about periods, no, we're not talking at the end of the sentence, right? But a lot of times a period is a cycle. And so we're talking about how long does it take for one cycle to actually happen. That's the same thing with the period of a wave here. How long does it take for one cycle to happen? It's going to be measured in seconds. Frequency is going to be the inverse of that, and we'll talk through what we talk about what that means in a second. So the number of cycles of vibrations per unit of time. So it's the number of waves produced in a given amount of time. It's going to be represented by a lowercase f, and it's going to be measured in hertz. Okay, so this is saying, hey, how many waves actually happen in 1 second? So if I go do, I just did like 10 waves in 1 second, so my frequency would be 10. If I do this, I would have like 1 wave in 1 second, and so my frequency would be 1. So the higher the frequency, what's the case? The more waves happen in a second. The lower the frequency, the less waves happen in a second. Now let's talk about that. If I have not a lot of waves happen in a second, what's probably the case with the period? The period is probably longer. Why? Because it's taking longer for one of these cycles to happen. If I have a high frequency, what's the case with this period? This period is really, really, really small. Okay? So the higher the frequency, probably the smaller the period. The lower the frequency, probably the higher the period. So if one goes up, one goes down, they're going to be inverses of each other. All right, so here's just a little information. You guys know I'm probably never actually going to test you on this guy's name, but just so you know, it's measured in hertz, capital H, lowercase z. Make sure you know measurements. We'll talk through more measurements. That's actually how we'll start the video tomorrow morning, just reviewing all of this stuff real quick. Okay, it's going to be after Heinrich Hertz. He demonstrated electromagnetic waves. All right, so we know it measures vibrations per second. So 1 vibration per second would be 1 hertz. 2 vibrations per second would be 2 hertz. 18 vibrations per second would be 18 hertz. 95 vibrations per second would be 95 hertz. Okay, then it gets a little tricky. Hey, what if I have like 45 vibrations in 2 seconds? We'll do in 5 seconds, actually, to make our math easy. Hey, that would be 9 hertz. Why? Because 9 waves would happen every 1 second. All right, and so hertz is actually going to be 1 over a second, which we'll talk through and discuss more later. All right, now, we can actually hear between 20 and 20,000 hertz. I know not every human is different, and if you think about it, any of you have a dog whistle. If you have a dog whistle, what's the case? That frequency is even higher. That pitch is higher. We can't hear a lot of that. Okay, and as you get older, I probably can't hear all the way as high as a lot of you can because I'm starting to get old. This isn't new information to anyone. Okay, and so, hey, this is actually the range that we can tend to hear. So, we've already started to talk about this, but how are frequency and period related? So the frequency is going to be the inverse of the period. And so what did we say that meant? As one of them goes up, the other one will be heading the opposite direction. So the frequency is the inverse. More vibrations that happen in a second, the less time each vibration takes, which means the wavelength is smaller. So if I have less vibrations per second, the more time it takes, which means your wavelength, your period is bigger. Okay, so the more vibrations, higher the frequency, smaller the period. The less vibrations, longer it takes, higher the period. All right, and so that's what we have there. Let's talk about wave speed. We're not going to actually get into the problems today. We'll start with problems tomorrow after we review. But let's talk through real quick what wave speed is. So let me get out of your way. There you go. If you need to pause that real quick. So the speed of a wave is equal to wavelength divided by period, or to frequency multiplied by the wavelength. Think about wave speed. What is speed? Speed tells me how fast I am actually going. Same thing with wave speed. It's going to tell me how fast the wave is actually going. Now, we might think that this depends on a lot of things, but it really doesn't, and we're going to talk through what I mean by that here in a second. So what are we asking? How far the wave travels in a certain amount of time. So remember, how do you find velocity? Let's think about velocity real quick. If I talk velocity, velocity was distance over time, right? We learned that at the very beginning of this semester. Now, let's talk through what we have for it. What is the distance that it takes? The distance of one wave is called the wavelength. How do we represent a wavelength? We represent a wavelength with a lambda. Remember, lambda represents wavelengths, and it's measured in meters. Okay? How do I represent how long it takes a wave to happen? That is called the period. How do we represent a period? We represent it with a capital T. Okay? So, what do we have here? Still, wavelength is measured in meters. Period is measured in seconds. So what is my velocity still measured in? It's still measured in meters per second. This isn't any new information from what we have done in the past. All right, so now let's talk through here. Real quick, it says speed of wave is equal to wavelength divided by period. So we said lambda divided by period. Now, we also said that period and frequency were inverses. And so another way that I can do this is I can just do frequency times the wavelength. All right, and I'm not going to go really into depth as to why that is, but period, remember, is just measured in seconds. The frequency is 1 over that. So really, if I have 1 over a second, there we go. We can just say the frequency. All right, so either one of these two is going to work. And let's actually talk units real quick. Hey, that's hertz, that's meters, but a hertz is just 1 over a second. So what would I still have? I would still just have meters per second. So that's why all of the units work, so it doesn't matter which one of those we use. So we got to look, hey, do I have the period? Do I have the frequency? And we're going to talk, we can interchange between those pretty easily. It's just a 1 over whatever the period is going to be how we find the frequency. All right, so that's what we have. Wave speed, how fast is the wave actually going? How fast is it traveling? So we're going to see a lot of what we already mentioned, and then we're going to talk more about other things here later. So speed was distance over time, measured in meters per second. Hey, look, what do you notice? We already said that right here, and I'm going to erase this now. Okay, so that's there, and then we talked about it. Wave speed is going to be wavelength over period. That's the lambda over the t. Okay, period's the inverse, so instead we can just multiply. And so then we said, hey, it could also equal frequency times lambda. All right, so that is going to be the case there. We are going to start out tomorrow by going through examples. We're going to finish section 2 notes tomorrow. And then on Friday, we will probably just have a day to do a review of all of this stuff and include more of the math type problems just to make sure we are good on that. All right, so don't forget, you need to do a couple things for me today. Number 1, you need to send me your notes. Yeah. Okay, send me your notes, make sure that gets done. Number 2, you got to give me a call, be ready to answer a question on the notes. If you have questions about anything, feel free to reach out, but you're all going to talk to me tomorrow anyways. So make sure that you call me tomorrow. Remember, you're not going to call me from like 11 to 12 because I'm going to be talking to my honors chemistry students then. Hey, have a great day. No homework tonight. Just send me your notes. God bless. Bye.